chapter is referring to the vegetation assessment and ecological point of view, how to address vegetation patterns and processes. And in our chapter, we just briefly introduce the methods that are typical for the vegetation monitoring. We did not really go into the technical details on the image acquisition and image pre-processing, orthomosaicing process, and these kind of georectification or the positioning and these kind of problems, because these are supposed to be addressed by the previous chapters, by the introductory chapters of the book. And so we look at we briefly introduce the methods like 2- and 3-dimensional mapping, and some kind of novel approaches such as fusion of the two, and combining with other techniques such as the field mapping, machine and deep learning, and open source. I don't know if I need to talk about the methods in detail, and you know yourself what 2-dimensional and 3-dimensional mapping is probably. So the 2-dimensional means that just we are using the optical remote sensing for optical sensors for the mapping and monitoring vegetation, and adding the 3-dimensional aspect brings us to the structure of the ecosystem. We structured our book on the different aspects of vegetation assessment, or the phenomenon that we can study with a UAS. We divided them into state, referring to the mapping the state of the ecosystem. Then on the structure, assessing the complexity and biomass and productivity of the ecosystem. And then status, referring to phenology and stress, and other status of vegetation of plant. And then the dynamics, which is monitoring the development, the changes. And in our chapter, we decided, because UAVs or UAS are very dynamic tool. They develop very fast. Sensors are developing. There are different new sensors every day. So we thought maybe the book would be good to serve as a practical book for those that want to do some kind of the UAS assessment. And that's why we used several pilot studies. We tried for most of the pilots to deliver also, or to produce also, or make available the data, the imagery, or the 3D information data that are related to the pilot, and the script, if possible. So the reader can himself download the data and try to run this case study himself. So for the state, we have 3 pilots, for the structure 1, and for the dynamic also 1. So the first, I just introduced briefly the pilots. The first pilot is monitoring plant invasions using OBIA, which is the object-based image analysis. You probably all are aware of what it is. So using the not only spectral but also spatial information, defining the objects. And in this pilot, we focused on the open source software. So we wanted to show what is the potential of open source software, such as and compared Ecognition as a classic commercial software for the OBIA with the Orphan Toolbox classification as a open source. This is an example for the giant hawkweed species. Then, for example, for pilot 3, we used the study that was published by Listen in 2015. where all the data are available for the reader to upload or download. And this was the multi-temporal imagery that was used for mapping species composition in temperate forests. So the main idea behind is that when we have the multi-temporal imagery of the same ecosystem, it is much easier to map to identify different species because they behave different way during the phenological cycle. So this is just an example of few of the repeated surveys, like 4 of the time slots during the year, where the individual species behave different way, and using machine learning algorithms. This multi-temporal imagery helps to recognize the species composition. This is a pilot. It's quite a nice, visually nice pilot for the structure. And this is a project of Austria, where in Klagenfurt in 2019, they made the artist Klaus Wickelmann made a temporary installation of forest grown in the inside the football stadium. Like, don't ask me why. It's just it just happened, and group from Austria did some 3D mapping on this stadium to reconstruct the 3D of the forest that was grown there. So this is an example of the point cloud that was derived, and this was done by the fusion of terrestrial laser scanning and photogrammetric point cloud derived from UAS. And this is an example of a pilot for serving to describe the dynamics, like the dynamic change in time. So this is an example from wind throw damage that was detected using a combination of aerial laser scanning and UAS or solar UAS data, solar photogrammetry. So it's actually a comparison of how these two can be, to what extent the photogrammetric point cloud can be used to assess the change done by withdraw damage in the forest. This is again in temperate forests. This study case is in Slovakia.
Hello, today I would like to talk about our work on the setting up some kind of framework on vegetation complexity assessment using unmanned aerial systems. This work was recently published in Ecological Indicators. It's a joint effort of our vegetation group within the Cost Action Harmonious. Within this large network of many countries, we realized there is a certainly need to set up some kind of general framework that would aim in standardizing and simplifying the process, making the general recommendations. For this purpose, we divided this the vegetation studies according to the component of vegetation heterogeneity that is addressed, ranging from species composition, stand structure, to the plant status. And of course, there's always a dynamic factor that can be applied to any of those 3 components. In any case, the approach is always driven and the plant mission should be planned according to the characteristics of the vegetation that is of interest. And also the survey and the processing should be adapted according to that. So for us going to the details for the plant composition, the species can show low or high similarity to the surroundings. For the composition, we are usually target for mapping biodiversity, mapping species distribution or habitat types distribution on plant vegetation types. We can also aim in mapping some specific species such as plant invasions or some species of specific nature in high natural value, like rare species or etc. So depending on the similarity to the surrounding, the species can be either showing low similarity or high similarity. In case of low similarity, it is easier to distinguish them from the other objects. It can be driven by spectrums or by the characteristics of the objects, and depending on those two types, also the processing would be different, either pixel-based or object-based. In case the species that we want to map is showing high similarity to the surroundings, we would probably need more sophisticated sensors, or perhaps some supporting structural information or other information or temporal resolution, and also we would have to apply some more complex models, such as combining object and pixel-based approaches. In case of structure, again, we have to look at the type of vegetation we would like to study. In case the vegetation cover is sparse, we can use passive sensors such as optical remote sensing, using high overlapping image acquisition and structure from motion algorithms. That will help us to derive point cloud and canopy height models out of it. In case vegetation cover is dense, like for example the temperate forests, we would need probably an active sensor such as LiDAR that would penetrate the canopy, and we will have information not only from the top of the cover, but also from inside from the ground. In such a case, we will have both the digital surface and digital terrain model, and we can easily derive canopy height model. In some cases, of course, we can combine the approaches. If we have the terrain model available from some LiDAR previous LiDAR mission, we can use the optical remote sensing for just getting the surface model that is up to date. Typical parameters that are assessed in this way are biomass, volume, or the stand complexity. The third component is plant status. It can be caused by both endogenous and exogenous factors. By the plant status, we understand like physiological status or phenological stage. In both cases, the approach would be different depending on how symptomatic and conspicuous is the phenomenon we want to study. It means how well it is visible or distinguishable from the data. If the phenomenon is easy to distinguish, we might be happy with the lower resolution data and more simple models, whereas in case it is not symptomatic, difficult to distinguish, we would need more sophisticated sensors such as high spectral, spatial temporal resolution, for example, hyperspectral data or thermal data, and more complex models, for example, deep learning. Typical parameters that would be derived out of this exercise are phenology or stress level. To illustrate our workflow and to make it useful, for easy to reach for others, we generated this kind of interactive workflow where you can look at different parts, and by clicking on the arrows you can open the different branches of the decision tree, and also some references and benchmarking studies that are to illustrate the process of each of the workflows. Okay, here is it. This diagram is available at both by the paper and also at the Harmonious website. Currently, we continue with this work, and we would like to study more the links between the type of the ecosystem and accuracy or the success of assessment using UAS to provide to populate our conceptual figures with the real data and real studies, and create some kind of benchmarkings for each of the types of parameters. You can also see some of our work in the book that is going to be published recently as an outcome of the cost action activities. Thank you for your attention.